Hello everyone. So we already have covered sensor parameters, and then we have covered the sensor physics as well. Followed by that, we also have seen what are the different technologies, fabrication technologies and characterization technologies associated with sensor. So now we'll slowly move towards the system associated with sensor. In our last lecture, we have seen the fabrication and characterization technologies associated with sensor. Just to brief on that, I would say that there are many different technologies associated with fabrication. For example, say in this particular course, we have seen what is microfabrication. But apart from microfabrication, you may find there are different other fabrication techniques that one should consider when they develop different devices. However, microfabrication is the kind of widely used techniques in order to develop different types of solid state sensors. To summarize the entire sensor fabrication technologies, I would suggest that you should go through technologies apart from microfabrication technologies, because recent days a new area of research has evolved, which is known as flexible electronics. So in flexible electronics, you may find that it's not only microfabrication techniques, but also some other techniques associated with sensor fabrication. It's better to say flexible electronics, this particular field is applicable for wearable as well as printed technology. So there are different printed technologies available for sensor fabrications, but it's kind of a combination of microfabrication and then some other techniques, and sometimes it's entirely other technique. To some extent, I have discussed this, some of this in different lectures associated with physics or example of sensing systems. But the idea is sensor fabrication is not limited to microfabrication. That is what I wanted to say. Apart from that, we also have seen different characterization technologies. So we have covered the important technologies associated with characterization or important facilities that are needed for characterizing different sensors. We basically covered the characterization techniques associated with morphological study of a particular sensor, for example ACM, TEM, AFM. However, there are several other characterization techniques, for example material characterization technique. Briefly, I have discussed what are the important material characterization facilities that one need for sensor development. And then there are electrical characterization techniques as well. I also have mentioned electrical characterization is very important, and I haven't discussed this in details because many of these techniques you already have used. For example, digital multimeter, to some extent maybe source meter or say LCR meter, you probably have used. But what is more important in this case is to understand what are the morphological characterization that is needed. Others are also important, but these techniques are kind of high cost facility, and that's why I have covered these areas in order to give you understanding regarding characterization facility. But just to point that out, that there are many other characterization facilities also important for different sensor characterization. Now we will slowly move towards the system. So again, in the system part, we will discuss the basics of the sensor system. and will provide you the basic understanding of sensor system that is usually used for fabricating the circuit associated with the sensor, because sensor alone cannot be used for certain application. For that purpose you need a circuit which should drive this particular sensor. So a typical sensor system looks like this. So it has a sensor, so it usually has a sensor, then it is connected to a signal conditioning circuit. Signal conditioning circuit comprises of a filter and an amplifier, broadly speaking. Then it is connected to an analog to digital converter, which converts the analog signal to a digital one. Then the output of analog to digital converter is sent to a processor. So a microprocessor takes a decision based on the signal that it receives from ADC, and then the processor sends the data to a memory or a display. So for example, if you take an example of digital thermometer, you will find that there is a sensor on top of a digital thermometer, more or less looks like this pen, and there is a temperature sensor on top, I mean at one end, and then it is connected to a system as it is shown over here, and then you will find there is a display. In that display you will see the value of temperature that has been measured by this sensor. Sometimes you can send that particular data to a memory as well, or both memory and display. So in certain cases you will find some digital thermometers have a option where you can see last 5 different measurements. So they actually send in that case the information to both display and a memory associated with that, where this thermometer stores last 5 readings that it has been taken or that it has taken. Okay. So this is a typical sensor system. Now in this course we will first look at the basic circuit associated with it. For example, when you have a sensor, you need a basic circuit in order to integrate this sensor with a system, which I have not explicitly mentioned in this block, but it's to some extent understood. Just to make it clear, we will first talk about some basic circuits, and then we will mainly focus on this signal conditioning circuit, filters and amplifiers, because signal conditioning is the first step towards a device fabrication or towards a entire system fabrication. So we will discuss filters and amplifiers. There are different types of filters, different types of amplifiers that one has to understand when a person tries to make a sensor system. And then ADC and processor part comes after that. So in this course we will limit our discussion to basic circuits in order to integrate a sensor to a system, then filters, and then amplifiers, or amplifiers and then filters, something of that sort. Okay. So one of the basic circuits associated with sensor system is a voltage divider, which is very basic, but it's very important when it comes to an resistive type of sensors. So a voltage divider is a circuit like this, where you divide an applied voltage into 2 different parts. So you have R1 and R2. Based on the values of R1 and R2, the applied voltage V1 will get divided. Say in this case, the voltage across R1 is V12, across R2 is V12, so you can consider V11, that is V1 that has been dissipated across R1. So it's V11, and across R2 it's V12. So your V1 is equal to V11 plus V12. So this is V11, and then you have say V12 across R2. In this case, we have taken V2 as the voltage across R2. So your V12 is actually V2 and your V in, that is input voltage, is V1. So let us do some simple calculations. So in this case, your R1 and R2 both are in series. So your total resistance of this particular circuit, or equivalent resistance of this particular circuit, is RT is equal to R1 plus R2. Now if you consider current flowing through this circuit is I, then I is equal to V1, that is applied voltage, divided by total resistance, right. So you can also say I is equal to V1 divided by R1 plus R2, because R1 plus R2 is your total resistance RT. So voltage drop across R2, that is V2 in this case, is equal to I into R2, because current flowing through this resistor is I and the resistance is R2. So according to Ohm's law, V equal to IR, that is V2 is equal to I into R2. Now you can put the value of I. Now if you put the value of I in this equation, it will be V2 is equal to, you can write this as R2 into V1 R1 plus R2. This V by R1 plus R2 is your I. So it's I into R2. So your V2 value is R2 divided by R1 plus R2 into V1. Hence, if you try to figure out what voltage you want to drop across R2, you can use this equation. Anyways, V1 is fixed, this is the input voltage. You just have to change the value of R2. Similarly, if you want to figure out what is the voltage drop across R1, say in this case it is V11, then it will be R1 divided by R1 plus R2 into V1. So this is the total, this is the voltage drop across R1. Now values of R1 and R2 you can vary in order to vary the voltage V2 and V11. So this is a voltage divider circuit that usually people use in order to connect sensors to a especially resistive sensors to a system. Another very important circuit is an Wheatstone bridge. Now Wheatstone bridge is a circuit where we arrange 4 different resistors in this fashion. So you have R1, R2, R3 and R4 connected in this way. And if you calculate the voltage, say this point is A and this node is B. So you can call this node as A and this node as B. Then the voltage at node A is VA, or potential of node A is VA, potential at node B is VB. Hence, the potential between node A and B is VAB. Okay. Now, if the bridge is balanced, then your VAB should be equal to 0 if your bridge is balanced. So, there will be no current flowing between A and B, because both of these should be in the equal potential. Now, if you consider only one part of this bridge, say this one, then it's a voltage divider. You have R1 and R2 connected in series, and then the applied voltage in this case is V in. So you can write VA, this is the VA, right? So VA is equal to R2 divided by R1 plus R2 into V in, right? Because VA will be the voltage drop across R2. Similarly, if you take the other half, your VB is nothing but the voltage drop across R4. So your VB is equal to R4 divided by R3 plus R4 divided into V in. So your VA is R2 divided by R1 plus R2 into Vin. Your VB is equal to R4 divided by R3 plus R4 into Vin. Now if your bridge is balanced, then your VAB is equal to 0. That means VA minus VB is equal to 0, because VAB is equal to VA minus VB. So this is equal to 0. Now put the value of VA and VB here. Then you will find R2 divided by R1 plus R2 minus R4 divided by R3 plus R4 whole into Vin is equal to 0. Now if you do this calculation, you will find that R2 divided by R1 plus R2 is equal to R4 divided by R3 plus R4. Do some more mathematical arrangements. If you do arrange this equation, then you'll figure out that R1 divided by R2 is equal to R3 divided by R4. That means if the ratio of R1 and R2 is equal to R3 and R4, then the bridge will be balanced. That means there will be no potential between, or the VAB will be equal to 0. So there will be no current flowing in this particular terminal, because both are equipotential. So you will find VAB is equal to 0. If you connect another resistor here, you will find the current is also equal to 0. In this case, you may replace one of the sensors with a resistive sensor. Now the advantage of that particular configuration is, say if this sensor, the resistive sensor, is kind of sensitive to any other environmental parameter, then these 4 resistors also will be sensitive to same environmental parameters, and because your bridge is balanced, then the factor due to these environmental parameter will get cancelled. So what actually people do, they consider one as the measuring sensor and then they keep another one as a reference sensor. So if there is any influence of environmental parameter in one sensor, then that will get cancelled out. So that way the Wheatstone bridge can provide you an extra advantage. However, if I discuss how this voltage divider circuit helps in integrating a sensor to a system, then it's again very simple. We already have discussed, say you have R1 and then you have R2. Now if your sensor is resistive in nature, then consider your R2 is the sensor. So you can connect one sensor in the voltage divider configuration and then you can apply a bias, say of 5 volt. Now because your sensor is resistive, definitely R2 will change, will increase or decrease in presence of a stimuli. For example, if you consider R2 as a temperature sensor, then the value of R2 will be a function of temperature. Say in this case it is increasing with temperature. So it will increase, say it's like 20, say to 80. So this is the calibration curve where your sensor temperature, or the response of the sensor increases with temperature. So at 20 this is the resistance value, at 80 this is the resistance value, whatever it is. Say it's 10 kilo ohm, and at 80 say it's 100 kilo ohm, for example. Now if you attach the sensor or integrate the sensor in a voltage divider circuit, R2 will keep on changing. So your V2, that is the voltage across R2, which is nothing but R2 divided by R1 plus R2, just now we have derived, into Vin. In this case, if your R2 changes, then your V2, value of V2 also will change. and then you can get that output in this terminal. Now you can connect this output to the next stage of your circuit, say a filter if needed, or an amplifier, whatever it is. Okay. Now you can connect this to the next stage of your system. So that is how you can actually connect or interface your sensor with the system. This is an example how these circuits can be utilized in order to interface your sensor with the system. Another example is like Wheatstone Bridge, as we have said. If it's an Wheatstone Bridge structure, if you measure say VAB, if it is A and B, and if you have say sensors connected here, one is for reference, another is the measuring, then if there is any mismatch between reference and measuring, you will get a VAB voltage. So you can also kind of monitor if there is any other influences present. And one of the very important advantage that you may get in case of Wheatstone Bridge structure is, if there is an influence here, the same influence will be applicable for this sensor, because both are same sensors, one is reference sensor. In that case, that influence will be cancelled out. If it is not getting cancelled out, definitely you will get a VAB potential, which will help you to modify your system accordingly. So these are the advantages you may get using those basic interfacing circuits, and that is why the interfacing circuits are very important. These are the basic circuits. There are many other circuits present, but I have just discussed two basic circuit associated with sensor interfacing. So we already have seen the interfacing circuits associated with the system. So one basic thing that we have discussed is the voltage divider circuit, and the second thing that we have seen is the Wheatstone Bridge. In both the cases, the idea is to connect a sensor with a system. So this is the basic step. In many cases, probably uh, it's not that much highlighted, but what I feel personally is this initial starting point of this system design is very very important, that how should we start. So that's why I have shown you both the possible options associated with the interface circuits. So once you have a resistive sensor, you should know how to add this sensor or how to integrate this sensor with the system. Anyways, in case of resistive sensor, the output that you get is in terms of resistance. So you have a resistive sensor here, then if you connect the resistive sensor with say multimeter, you'll get that the value that you are receiving as an output from this sensor is the resistance, right? Now how we can connect that resistive sensor, or in other terms a resistor, with a system, because ultimately you need to connect this sensor with a system, right? Now this is the basic way of doing it. You can either connect this with voltage divider circuit. I have explained before as well, but just concluding that you can connect this with a voltage divider, connect it in a voltage divider circuit, and then you take the analog output from here, and then you connect it to one say amplifier. This can be filter, and then finally after this signal conditioning, you connect this with a say microcontroller or microprocessor, whatever it is. So you can connect it with a microcontroller or a microprocessor thereafter. But when you are connecting the sensor in a voltage divider circuit, it's also very important to decide what should be the other register. So again, there is a consideration that you should keep in your mind. What is your bias voltage? If it is 5 volt, then your R1 will be decided accordingly. If it is 3.3 volt, then you can decide your R1 accordingly. But I mean, in both the cases, the R1 can be same. It's not the issue, but here you are actually dividing the entire bias voltage into two different parts, and the first part is the one which will decide what will be the second part. So one way to do the entire calculation is to first check what is the resistance range that your sensor shows in response to the stimuli. Say the resistance varies from 10k to 100 kilo ohm. Okay, so if the resistance is varying from 10 to 100 kilo ohm in response to the stimuli, if it is in temperature sensor, so say in the temperature range from 20 to 80 degrees centigrade, this is how the resistance varies. So in this case, your R2 value can be 10 kilo ohm least and 100 kilo ohm maximum. So here, when it is 10 kilo ohm, you will get one sort of output for a fixed R1 value. So now you can fix your R1 value, say 10 kilo ohm only. So when the output of your resistor is 10 kilo ohm, the entire 5 volt will get divided into 2.5 and 2.5, right? Now when it is 100 kilo ohm, then this particular value will become 100 kilo ohm, right? Now if it is 100 kilo ohm, this is 10 kilo ohm, so accordingly it will divide by 1 is to divided in 1 is to 10 ratio. So the majority or the maximum voltage will drop against this 100 kilo ohm resistor. So your range of this voltage across R2, that is if you take VO, the range of VO will vary from say 2.5 to say something around 4.5 or something. You just check 1 is to 10 what would be uh, the voltage across R2. Now this is your voltage window, and that voltage window is your operating voltage window. Now based on that only you will decide your amplifier, filter, whatever it is. Okay, now if it is 3.3, then again it will be, the window will be even lesser. More the bias voltage, more will be the power consumption. So you also have to decide. You can't put here 15-20 volts, because in that case the entire system will take a lot of power. So there is a trade-off where you can sit and decide what should be my minimum bias voltage to get a reliable set of output. So that is what you have to decide. Same goes for the Wheatstone Bridge circuit as well, because in both the cases you have to bias the circuit, and as far as the bias is concerned, it actually decides how much power your system will draw from the power supply. If you are planning for a wearable device or this wearable sensor, you just can't say that the power consumption is very high, because in that case you have to use a battery. If you are using the mains, then to some extent it's okay that you are taking power from AC mains. Even the power is in the higher side, still it is to some extent justifiable, although it's always recommended that you make a low power device. But if it's a wearable sensor or a sensor that will draw power from batteries, you have to also take these bias voltages, these resistance values into consideration, so that you can make the system which will draw the minimum power from the battery, and that also will actually help to increase the lifetime of the entire system, lifetime of the battery. That means with a single battery you can run the device for say 2 months, 3 months, something like that. So these are the considerations in practice that one has to uh, take care in both the cases. However, in this case you have an extra advantage of getting read from the environmental effect. So the environmental effect can be minimized. In fact, in the coming lectures I'll show you the entire thing in a, with an experiment. We'll do a small experiment and we'll see how these circuits are different and how they are providing advantages uh, as far as the system is concerned. So this is the basic circuit which will allow you, or maybe the starting point of the entire system design. In the upcoming discussion, We will discuss what is amplifier. Amplifier again is a very important component of the entire sensor system, and amplifiers are of various types as well. So, we will discuss some of the very important types and we will see what is the characteristics of amplifiers and how amplifiers will help in say measurement or developing a system and why it is important. Till then, thank you.